Morning to all of you. Today, sir, we are live.
Right, right. Oh, thank you.
Okay, sir. So, just I want to like to introduce our expert. Today we have the Mr. B. A. Oja sir, Professor B. Oja sir. He is the retired from the BBM, and he has published a book also for the power system protection. So sir is a master for the power system protection. We will try to cover today's generator protection, and end of the session, if anybody have doubt, please message me on my personal WhatsApp number, which already given in the WhatsApp message. So now we will request sir to start the presentation. Pooja sir, please, you can start.
Good
Sir,
afternoon,
you can
everybody.
start now.
Uh, right. Good afternoon, everybody. Uh, I am Bhuvanesh Oza, uh, meeting everyone through air, through online medium for the first time. This is my first trial, thanks to Parul University and Hethel, that I am meeting you in this particular way for the very first time. This is my first trial. We are going to talk about uh, the concepts of generator protection. I hope you are seeing the slide of the generator protection as it is seen. Uh, the protection of generator is in a way little complicated, because if there is a fault in the transmission line, then just stripping the breaker to isolate the fault is sufficient to clear the fault. That means the faulty part will be isolated from the remnant of the healthy system. If you just trip the breaker, in generator it is not like that. In generator, if you trip a breaker, that means generator is connected to bus via breaker. If you trip the breaker, the fault will not be isolated, because if there is an internal fault in the generator will keep on feeding its own fault. Therefore, not only tripping of the breaker, but you have to trip the excitation system, you have to disconnect the excitation system, you have to uh, trip the turbine, that means the turbine has to be stopped. One has to trip the boiler, one has to trip all auxiliary motors, all main, particularly 6.6 kV motors like primary air fan motor, boiler feed pump motor, uh, FD fan motor, ID fan motor. That means all auxiliaries, they have to be stopped. Complete power station will come to a halt whenever there is a fault within the generator. Therefore, the whole protective system is going to be comparatively quite complicated. And with reference to that, with reference to tripping of a generator, usually the protective scheme is divided into three different parts. Right. So before we come to that, uh, we let us have a look at the major faults and abnormal condition in case of generators. Uh, you are seeing the slide in front of you. Failure of insulation of the stator winding. That means if the insulation fails in the stator winding, failure of insulation of the rotor winding, uh, unbalanced loading of the generator, field failure, that means field of the generator which is connected to the bus page. If the generator is overloaded, if there is an over voltage in the generator, if the prime mover of the generator fails, then if the synchronism is lost, if there is over speeding, if the frequency of the whole system comes down or goes up, right? Under frequency particularly is for frequency coming down, overheating, if the generator winding is overheated. So these are the major faults and abnormal condition in case of generator. Uh, the the next slide is what are the protective schemes employed for generator? What differential protection of generator, inter-turn fault protection, stator earth fault protection, overcurrent and earth fault protection, uh, rotor earth fault protection, negative phase sequence protection, field failure protection, overload protection, overvoltage protection, reverse power protection, full sleeping, backup impedance, and underfrequency. Uh, this much, these many protections will take about, I think, not less than 8 hours to cover. Therefore, it will be difficult to cover all these protection in an hour. We'll be trying to cover as many protections, if possible, 3 out of these in today's talk. So, as I was talking to you, the different kinds of protections, as you can see on your screen, are class A, class B, and class C protections. The protective schemes are divided into three major classes. Class A is for very severe faults within the generator. That means if within the generator, and now I hope you might be knowing that the generator is connected to generator transformer directly. Usually in a unit system of generation, there is no breaker between generator and generator transformer. Therefore, if there is a fault in generator transformer, that also is equivalent to a fault in the generator. Similarly, two unit auxiliary transformers or one unit auxiliary transformer, as the case may be, unit auxiliary transformer is feeding all the auxiliaries of the generator. You might also be knowing, probably you would have studied in the different kinds of types of generations. Might have studied the thermal power plants, in which you would have studied that the power plant requires 10% of the power that is generated for running its own auxiliaries. So that is fed through unit auxiliary transformer. So if there is a fault in unit auxiliary transformer, that also falls in the generator fault. Therefore, if there is any fault within the generator, any kind of fault within the generator, it is usually very severe and it results in a very severe damage. Therefore, in this case, the class A protections will operate. In this class A protection, what all is there, you can see on the screen. That means when the class A protection operates, the actions taken or the sequence of action is this: that first, see, that means not the first, or everything will happen simultaneously. Generator breaker is stripped, generator field breaker is stripped, that is, field is disconnected. Incomer breakers of unit auxiliary transformers, that means the breaker between unit auxiliary transformer secondary and a 6.6 kV unit bus will be tripped. Tie breaker between station bus and unit bus will be closed. Boiler trips. Boiler tripping means the flames to the boiler. That is the flame that is being fed by the burners. Those burners are tripped. No coal will enter the boiler, no air will enter the boiler, so that the flames are extinguished. That is the meaning of tripping of the boiler. Then prime mover trips, that is the steam stop valve is closed so that no steam enters into the turbine. All unit auxiliaries are tripped, that is PA fan motor, FD fan motor, ID fan motor, all unit auxiliaries are tripped, and class A trip annunciation appears. This is a very small list of the events that is happening because of class A trip. As such, I have explained, or I have shown about 7 events here, but there are So to say about 48 events occurring whenever class A protection trips. It's not possible at this juncture to go into so many details of what all is happening when class A trips. But class A trip is a big happening. Class A tripping in the power plant is a very big incident because once the boiler trips, it's very difficult to bring back the boiler. It's very difficult to bring back the unit to the bus. Uh, the record breaking time, which one of my friends who was at the then time executive engineer in Vanakbori thermal power plant, he was telling that the record breaking time within which he brought the boiler, I mean, he brought the unit 210 megawatt generator on the bus was about 1.5 to 1 hour 35 minutes. So it's a big long time. If the boiler comes to rest, if boiler comes to room temperature, then it takes 7 hours to rebuild the boiler to its normal temperature because the boiler uh, boiler temperature near the furnace is of the order of some 1100 degrees centigrade. Therefore, bringing back the boiler to normal condition is a very big time and quite a lot much of revenue will be lost. Therefore, if class A trips, it's a very big event. But if the damage is going to be very bad, then class A is a must. Class B is little different from class A. Class B type of situation will come only if the fault is not very severe, particularly if the fault is outside the generator, and therefore the complete tripping immediately is not desired. Therefore, what is done is we make the use of the kinetic energy of the generator in this case, because when you tripped class A, the complete load was lost. Therefore, there are chances of generator uh, accelerating. There are chances of overspeeding of a generator. I would remind you here that the speed of the generator for steam turbo alternators in the thermal power plant is some 3000 rpm, and I so often tell to the students that if at all you cannot appreciate 3000 rpm, then I would talk in terms of rps, that is revolutions per second. At 3000 rps comes to some 50 rps, 50 revolutions per second. In a second, a dynamic mass of some 200 to 50 tons is rotating 50 revolutions. So such a generator which is already running at this high speed, if it accelerates, if its speed becomes more, then the rotor parts will be damaged. So you are trying to trip, but then you are damaging the rotor parts of the generator. So therefore, in actual case, in the actual generator, whenever class A trips, there are special braking systems which break the rotor. So as I was telling to you, class A trip is a big event in the power plant. Class B, we make use of the kinetic energy of the generator. That is, we don't trip everything. As you can see on the screen, in case of class B trip, uh, boiler is tripped and turbine is tripped. That means we trip the boiler, that is the flame are extinguished, all flames are extinguished, and the steam stop valve is closed. Therefore, turbine will not run. Then what will happen? That the mechanical energy from turbine is not available to the generator. Generator is connected to bus. Therefore, the electrical power also will slowly go on reducing. Say if it is a 200 megawatt generator, then it will from 200 megawatt, it will go to 150, then 100, then 50, 25, like that. And before it comes to zero, at about 0.5% of forward power, the low forward power protection will operate. Low forward power protection is class A, or if you don't understand low forward power, let us use the word reverse power, right? That means the power will reverse. Reverse means the power was being fed to the bus. Now, bus will feed the power to the generator. Generator will start watering. at this juncture, the class A protection will operate, and class B, in a way, finally is going to result in class A. But then we have made the use of the kinetic energy of the generator, of the large inertia we have made use of, and we have avoided the possible damage to the rotor parts of the generator. Not only rotor parts of the generator, but the rotor parts of the turbine as well, because you might be knowing well that the generator rotor is run by three stages of turbine: the HP stage, the IP stage, and the LP stage. Therefore, so all the three stages, I mean, everywhere, all rotor parts are accelerating. So this we are avoiding in the class B. So this is what is happening in class D trip. Class C is very simple protection. Class C is there is a fault on the line. Generator, then generator breaker, and then there is a bus. From bus, many lines are emanating. Some 8-10 lines are emanating. On one of the lines, there is a ground fault or line-to-line fault. So if there is any kind of ground fault or line-to-line fault, the line relays must operate. If the line relays fail, actually, you might also be knowing, if you have studied the protective systems well, you might be knowing that for a transmission line, there is a distance protection. If distance fails, then there is a backup overcurrent and earth fault. If that fails, then the fault is rather thrown to the generator. Actually, in that case, there is a protection in transformer secondary backup protection, right? If that fails, then only it will result into class C. That is, then the generator will see the fault, and then if that happens, the class C protection operates. In class C, we only treat the breaker. We don't treat anything. We keep the turbine running. We keep the boiler running. We keep all auxiliaries running. Generator will run on its house load, that is 10% of the rated power that is required for the generator itself. Generator will keep on running on the house load, and connecting the generator back to the bus takes hardly 5 minutes or less than that, because it needs only synchronizing the generator to the bus. Therefore, a lot of time which otherwise is lost in class A or class B protection is saved in class C. In case of the generator tripping, in modern steam or modern thermal power plant, there is a facility of, so to say, HPLP bypass system. That is, the steam is being generated by the boiler, but it is not given to the turbine. Only part of the steam is given to the turbine. The remnant steam will be bypassed. It will pass through many pressure reduction stages, and then it will be sent back to the condenser. So such systems, HPLP bypass systems, are also there, and all these systems help in a way so that you are not to trip the boiler, because tripping of a boiler is a big event. Therefore, what we do, I hope you will be able to appreciate that if class C protection, why these different classes, class A, class B, and class C. In class A, we are lost, we can't help it, and we have to trip everything. In class B, we make use of the kinetic energy of the large mass, and in class C, we are not tripping anything but breaker. Therefore, these are the reasons why the generator has these three different classes of protection. So, I was telling to you that the generator protection system is that way quite complex, right? So, forgetting about this now, these complications, let us go to one kind of protection. That is the first kind of protection, the failure of insulation in the stator winding. Why should the insulation fail in the stator winding, right? What are the causes? So we must know as to how many causes are there. So for any kind of protection, we will have to study so many things. Causes of the problem, uh, the consequences of the problem. If we don't take action, what are the consequences? And the third thing, what is the protective scheme to get rid of these problems? Uh, so failure of stator insulation is due to many causes. One very obvious cause is overload. That means if the load of the generator is more than the rated load, that means large current will flow more than the rated current. When I speak of rated current, I am reminded that the normal rated current of 210 megawatt 15.75 kV generator. I am speaking all these figures which are standard and typical figures. 210 megawatt is one of the standard capacity of a generator. 15.75 kV is the voltage rating, and for this 0.85 power factor, the rated current itself is 9050 ampere. Uh, I hope you should be able to imagine the heat dissipation required with reference to this normal current which is passing 24 by 7. That is for all complete time. For the total time, this much current is passing. If the current goes beyond that, then the generator winding will be overloaded. And because of that, the insulation can fail. The another reason is the ventilation system failure. I was talking to you that 9050 and 9050 ampere is for 210 megawatt generator. Nowadays, 210 megawatt is comparatively a smaller capacity. People talk of. You might be knowing that at the Vanakbori thermal power plant, there are 7 units of 210 megawatt units each, and 8th unit is of 800 megawatt capacity. Single unit of 800 megawatt capacity. So 800, 1200 megawatt are the modern capacities. Let us not talk about 800, but if I talk about 500 megawatt capacity, the rated normal current is 17,000 amperes. 17 kiloampere is the rated normal current. To dissipate the heat, the stator conductors are made hollow. I hope you understand hollow. The stator conductors are hollow, and through the hollow, the distilled water is continuously run. The pressure, temperature, and flow of that distilled water at the entry and at the exit are measured continuously. If any of the parameters go out of the way, then the protective system has to, alarm system has to operate, right? Therefore, this it is very quite complicated and a big business to dissipate that heavy amount of heat that is produced, because if 9000 ampere is the current, the heat is going to be proportional to 9000 square, that is 81 into 10 raised to 6 I am talking about. Therefore, large amount of heat is going to be produced, and we have to use distilled water because normal tap water is conducting, it is electrically conducting. Therefore, we have to use the distilled water, and the space between rotor and stator, the the air gap, it is not air gap. Air is not used. Hydrogen gas is used. The space is cooled by hydrogen. Hydrogen is very light gas. The windage losses due to hydrogen is 10% of that of the windage losses if air would have been present. Hydrogen is a very special gas. It is electrically insulating and thermally heavily conducting. Therefore, uh, hydrogen is used to carry away the heat. If this hydrogen cooling or water cooling system fails, then also the insulation will fail. If there are over voltages, right? Over voltages, that is power frequency over voltages or high frequency over voltages, then also insulation can fail. So there are enormous reasons for insulation failure. Where is the insulation? Insulation is between two conductors of different phases, that is between R and Y and between Y and B. Now, how can the insulation between R and Y fail? And if R and Y insulation fails, then there will be an RY fault. If the insulation between Y and B fails, then there will be YB fault. Now, the generator design is such that the two different conductors of the same phases are never kept in a single slot. Therefore, RY or YB fault in a generator slot is not possible. But that is possible in the overhang portion. Overhang means the conductors are going from slot number 1 to slot number 7, and that is going behind the generator. That is known as overhang portion. And this overhang portion, there is R is crossing Y or Y is crossing B. So there the insulation between R and Y can fail. And there can be a failure of insulation between phase and ground. And this is possible in generator slots also. So that is line to ground fault. So we have to talk about both kinds of faults, double line and line to ground. So for such faults, and we shall see if the time permits, that for line to ground fault, a very different kind of protective system is used, because line to ground fault is passing through the stator laminations, and if the large current passes, say for 15.75 kV generator, if we don't restrict the value of the current, then the current can be in terms of thousands of ampere, some 15,000 or 17,000 ampere or even more. And in that case, the generator stator laminations would get sintered. They would be connected together. That is, sintering means they are welded together. Welding would happen, and it would need quite a long time to repair such a stator. Therefore, the stator current due to stator earth fault is reduced to a very small value so that it cannot damage. Those who are seeing such schemes for the first time, they would be getting exclaimed that the generator which has got rated current of 9,000 ampere, the earth fault current for the terminal earth fault is limited to a value of 2 ampere. 2, simple 2. In the primary side, I am telling, right? So the current reduces to a value of 2 ampere, and 2 ampere in the primary. When it goes to secondary, say 9,000 ampere is the stator current. Therefore, these CTs which you are seeing in your slides are 10,000 by 5 ampere. So the current reduces to 10,000 by 5 means 2,000 times less. 2 ampere would reduce to 2 or 1 milliampere, and 1 milliampere cannot be sensed by any overcurrent relay. So stator earth fault is a different kind of protection. This differential protection, the slide of which is against your screen, आपके स्क्रीन के सामने जो आप स्लाइड देख रहे हैं, उसमें in that slide these CTs have ratio 10,000 by 5, and this protection is meant only for line to line or triple line fault. The winding that is shown is for a single phase. Such 3 phase windings are there. For 1 phase winding, the circuit is shown. The circuit is wired like this. You can see the dot on the CTs that shows the polarity. That means CTs have to be connected with correct polarity. The principle is very simple, that the primary current I1 and I2, as they are shown, capital I1 and capital I2, flowing through the generator winding. I1 is on the neutral side, I2 is on the line side. They are having the same magnitude if there is no internal fault. That means if there is an external fault, or if the rated condition is there, I1 and I2 are the same. So small I1 and small I2 flowing in the pilots. The wires which are connected in the secondary CT are known as pilot wires. The current I1 and I2 flowing through the pilot wires is same. Therefore, I1 minus I2 flowing through the instantaneous overcurrent relay is 0, and therefore no protective scheme will operate. Right? Double line fault, if at all it occurs, then the magnitude of the double line fault will be very large. Uh, if you calculate based on the positive sequence and negative sequence impedance, uh, then it would be of the order of some 333%. That is, from 9,000 ampere, it would rise to some 27,000 or 30,000 ampere. And this large current is dynamically damaging. Dynamically damaging means generator would just burst within cycles. Therefore, double line fault is a very dangerous fault. It has to be taken care of very fast, very immediately, and therefore we are using the instantaneous overcurrent relay. If there is an internal fault, then this balance between capital I1 and capital I2 is lost. That is, I1 is not equal to I2, small I1 is not equal to small I2. I1 minus I2 will flow through the instantaneous overcurrent relay. The relay will operate and it will initiate class A protection system. This is, in short, differential protection, my friends. The differential protection described so easily is not this very easy, because you have to fulfill these requirements. First requirement is very obvious, that CT1 and CT2 have to be connected with correct polarity. If you connect with wrong polarity, then instead of I1 minus I2, small I1 minus small I2, small I1 plus I2 will pass through the relay, and relay will operate when the rated current is passing through the generator, which is wrong. But this correct polarity is only a process to be taken care of while commissioning, means while first wiring the protective scheme. This wiring of the protective scheme is also a subject by itself. This project engineering, that is installation and commissioning, if somebody learns, you can earn money, you can start business based on this, and one has to be very careful. So, how to check the polarity of cities, that also one has to learn if you are thinking of becoming a commissioning engineer. But forget about these things right now. First requirement is this. The second requirement is, the differential protection shall operate sensitively for internal faults, and it shall remain stable against external faults. This is a very important requirement, that the protective scheme is only for internal faults. External faults are certainly faults. They are also dangerous, but differential protection should not operate for external faults. The differential protection means that there is something wrong with the generator within, and you have to take care for the generator within, anything that happens within the generator. It is not the right time to discuss about these things now, but I have many of my friends who are working in the as a maintenance engineer in large power stations. Whenever a differential protection operates, they never doubt the within of the generator. First, they will always doubt something wrong outside. There are many case studies in which the differential protection is operated for faults outside the generator. So this is the study by itself, and we have to talk at length such case studies. I am unable, because I do not have the relevant slides right now. Otherwise, I could have shown here also. And for a diploma student, it is too much of a study, so I would leave it aside. But this is very important, that for external fault, if this system operates, you will be misled. Therefore, for external faults, this system has to be stable, means it should not operate for external faults. It should operate only for internal faults. But this is not very simple. For system not to operate for external faults, both the cities. In the earlier slide, I had shown CT1 and CT2. CT1 on the neutral side, Shall I take the earlier slide? The CT1 in front of you. CT1 is the CT on neutral side. CT2. Both these CTs have to be perfectly identical with reference to their saturation characteristic. Two different CTs to be exactly identical is never possible. No manufacturer can manufacture such two CTs very identical, and therefore uh, under normal condition the CTs are working in the linear region of their saturation characteristic. But when the external fault occurs, the CTs are giving different open circuit voltages, and therefore they are injecting different currents, small I1 and small I2, and I1 minus I2, that is difference of current, will be present, and this can mal-operate relay because there is no internal fault. To take care of this condition, we have to connect a resistance in series with a relay, and that resistance is known as stabilizing resistance, because two exactly identical CTs are never possible. Another problem is this, that another requirement is this, that the points A and B, as shown in, I hope you are seeing the slide in front of you on your screen. A and B are the points. There should be equipotential, that is VAB, voltage between A and B should be zero. This is also not possible because physically the relay is in the control room, CT is on the turbine floor, and CT1 to relay and CT2 to relay. I mean, for A and B to be equipotential, CT1 to relay and CT2 to relay, this distance has to be same, which is just not possible because of geography of the power plant, and therefore points A and B cannot be equipotential, and because they are not equipotential, current will pass through them, and the mal-operation of the differential protective system can occur. And to avoid this, once again you have to connect the stabilizing resistance in series with the relay coil. This is a very important requirement. So that's how the differential protective system, which has been discussed in a simple way, goes on becoming complicated. The last requirement is differential relay should be immune to harmonics. It should not operate for any other current other than fundamental. And the harmonics are present if there is an overvoltage surge. So the relay has to be made immune to these overvoltage surges. That means it should be made immune to the surge currents. So what do we do for this differential protection? What we do is this vector diagram, as it is shown, EMF of CT1 E1, EMF of CT2 E2. If you take out the CT secondary resistance, the output voltage, terminal voltage at CT is V1 and V2, and if you cross these points, the point at which the relay is connected, at that point the voltage is zero, and it should be zero. But as we discussed, you cannot connect the relay exactly at the midpoint, therefore the voltage will not be zero, and mal-operation in this case has to be avoided. The next slide is showing to you for internal fault. For internal fault, E1 and E2 has the same direction. A large current IZR, that is IZR is the voltage drop across relay, and I is the current flowing through relay, so relay will certainly operate. And to avoid the large voltage across the relay, we have to drop some of the resistance in stabilizing resistance. So IR step is the voltage drop in the stabilizing resistance. So this is the diagram. This vector diagram is for internal fault. This vector diagram against your screen is for external fault, and this diagram is for internal fault. In actual scheme, we connect the stabilizing resistance. I hope you are seeing the figure in front of your screen. and this figure is showing certain uh, uh, parameters of the equivalent circuit of the CT. So to say LM1 is the magnetizing shunt magnetizing inductance of the CT1, LM2 of CT2, RCT1, CT secondary resistance of CT1, RCT2, CT secondary resistance of CT2, RL is the lead resistance because you will have to connect physical wires from CT to control room. So that is RL. RR is the relay resistance. LR is the relay inductance. LR for the high impedance relaying. Such a kind of differential relaying is known as high impedance differential relaying, in which we connect large resistance in series with the relay. So in such high impedance relaying, LR, the inductance of the relay is usually so small that you can ignore, right? So we will consider only RR, and R step is intentionally connected in series with the relay to avoid mal-operation in case of external fault, as we have discussed, to avoid the mal-operation due to CT saturation mismatch due to non-identity of two cities, right? And the relay not being able to be connected at exact midpoint. For that, we connect the stabilizing resistance, large stabilizing resistance in series with a relay. So I will just show you hurriedly as to how to calculate this R step, because this is an exercise for relay engineers. This is the exercise for switchgear engineers. They have to find out the value of RR, for which they need all data. What all data is needed, that we will be seeing in the next slide. Uh, yes. So what you need is this. We consider one of the CTs as badly saturated, flat saturated, that is CT2 is shorted, LM2 is 0 and LM1 is infinite. That is the worst possibility. And in that case, IF that is shown is the fault current. So you need the value of the fault current. Fault current for large generator is usually 5 times the rated current, because the subtransient steady state reactance XD double dash is of the order of 20%. And for IF would be 5 times the rated fault, that is the current. Fault current is 5 times the rated current. 45,000 ampere for 210 megawatt generator, and as it comes to the secondary small IF, as it is shown, is 45,000 divided by 2000, that is 22.5 ampere. RCT, CT secondary resistance, you have to ask to CT manufacturers, they provide you that value. RL you have connected, so you know the value because we have connected the lead wires, therefore we know the value. RR you have to ask to relay manufacturer what is the resistance of the relay. Based on this, you can always find the value of R step by this formula, the formula that is presented against your screen. It is coming from a simple Ohm's law. So that R step is equal to IF into RCT plus RL divided by IS. IS is the setting of the relay. The differential relays for generators are usually set at 5 or 10%. It is for a 5 ampere relay, we set it at 0.5 ampere. If the current is more than 0.5, then the system will operate. So upon IS minus RR. So this value one has to calculate, and this has to be connected. This value of this has to be connected. And you have to have the correct value of the knee point voltage, that is the knee point of the CTs. VKPV should be IF into RCT plus RL. So if you buy good CTs, then the saturation of the CTs will not be a problem. Right. So this kind of a relay is used. I would not talk of this relay because this is a very old relay, CAG version of the English electric. Now people are using numerical relays, so let us not talk about this. So this is the description of the relay. We'll not talk about that. This is a detailed three-phase diagram. You can see large generators, 210 megawatt large generators are having the double star winding, because in one winding you are passing 9000 ampere. Therefore, rather than passing current 9000 ampere through single winding, we divide the winding into two parts, two parallel winding. So through each winding only 4500 ampere passes. That reduces the problem of heat dissipation. So double star winding is shown, and the CTs for differential protection are connected as shown. 6 CTs are required, you are seeing, and the relay 87 GR, 87 GY, and 87 GB. Slowly you will have to be conversant with these numbers. These numbers are NC numbers, American National Standard Indexes. They are internationally known numbers. 87 is for differential relay. 87 G means generator, R by B phases. The stabilizing resistances are also shown. 87 and stabilizing resistance are bypassed by what is known as SD, surge diverter. The surge diverter bypasses all high frequency signals. That makes the relay immune to harmonics. The requirement is fulfilled by connecting surge diverter. Surge diverters are nothing but the nonlinear resistances. These nonlinear resistors, uh, nonlinear devices, provide high resistance when the normal fundamental frequency current is passing, and they provide very small resistance, practically short circuit, when high frequency signals are passing. You can see that the neutral of the generator is connected to neutral grounding transformer to a reactor. That reactor is of 1 ohm, and that 1 ohm, when it is reflected to the primary of NGT, neutral grounding transformer, is of the order of some 4000 ohms. And this value, 4000 ohms, will restrict the earth fault current to a value of 2 ampere, as we were discussing. You cannot connect the reactor directly in series with the neutral point, because then 4000 ohms, such a large ohmic value, would not be feasible technically. And that too, when 2 ampere is passing through 4000 ohms, the voltage neutral rises to a voltage of 8 kV. So this such a high voltage reactor design is also not feasible. So this kind of earth connection is made, that is, earthing is done through neutral grounding transformer. Neutral grounding transformer is just a distribution transformer. A typical uh, rating 15.75 kV primary, 240 volt secondary, and some 15 kVA. Right? It's a small distribution transformer that is used. So these values also can be calculated by the design formulae, but we would not go into these details right now. So I go to the next slide. So this slide shows the detailed three-phase drawing. The next drawing is showing to you the next drawing is the DC control circuit, that is operation of 87 GR1, GY1, GB1. That means any of the relay contacts operates. 86 G1. G1 is not written, but you have to read 86 G1 means the class A protection trip relay. It will operate and class A trip will be initiated. Differential protection is a protection for double line faults, and it's a very severe fault, very immediate action, and this action will trip the complete generator. So the next drawing is next slide is how to calculate the value of relay setting. I skip right now. I hope if the Parul University management provides to you these slides in form of email, then you may see these emails and you can have all the slides with you. The slide in front of you in your against your screen is the numerical approach. That is, uh, in numerical approach, we don't use high impedance differential relaying. We use low impedance differential relaying. That means instead of uh, stabilizing resistance, we use the restraining winding, that is the third winding in the relay, the operating coil and restraining coil, as you know, right? So we use a operating coil and restraining coil, and the curve, as it is shown on x-axis, is a stabilizing current, that is what you call I1 plus I2 by 2, and on y-axis is I differential, that is I1 minus I2, and the curve is like this. First part is A part, that is basic setting. Second part is B, that is first slope, and third part is C, that is another slope. So the numerical differential relays provide these two different slopes in the differential protection. The first slope takes care of maloperation due to CT errors, and slope 2 takes care of the maloperation due to saturation of the CT due to high fault currents. So the numerical relays use low impedance differential relay. The, the next slide, uh, the next slide is the talking about the same thing. Uh, the next kind is inter-turn fault protection. Now you see the inter-turn fault protection is the fault between two turns of the same phase, because we have a double star winding. If there is a fault between two turns of the same phase, then differential protection cannot take care. The differential protection which we talked about cannot take care, because current through CT1 and CT2, even if there is a fault, will be same. So what is used is such a kind of transverse differential protection. That means once again, 6 more CTs are used. 6 for differential protection we have seen, 6 for inter-turn differential. That is, they are wired like this, as seen in the, it is a kind of differential protection only, 87 GIR, 87 GIY, and 87 GIB. If there is a fault between two turns of the same phase, you can see that there are two windings of R phase shown. Between two windings of R phase, if there is a short circuit, then the current flowing in the upper city and lower city of the inter-turn differential will be different, and that will give rise to current flowing to the relay, and relay will operate. Inter-turn fault itself is not a very damaging or dangerous fault, because it does not generate very large current, right? So it is not a problem of any big overheating or any big problem, but there will be a problem of local heating wherever there is a fault. Fault means there will be a small arc. So whenever there is an arcing, there will be local heating, and that local heating will finally result into line to line or line to ground fault. Therefore, uh, we don't wait for line to line or line to ground fault, but we treat only when the interturn fault occurs, and this interturn fault also is a fault within the generator, and therefore it is class A protection. Relays used are instantaneous overcurrent relays once again. So the next protection is stator earth fault protection. In my mobile, I am seeing that 7 minutes are left. Within 7 minutes, I can introduce stator earth fault protection. I cannot fully talk about stator earth fault protection. If your university, or I don't know how many participants are hearing me, I so learn that many participants in and across the nation are probably hearing this lecture. There are many student friends who are just hearing me out of recalling their early days memory of the studenthood. Therefore, they would be knowing all these things. So, if somebody, some other university or our university itself designs such a webinar, if this lockdown situation continues, then or if lockdown ends, then we'll be able to physically talk when if at all I'm cold. So, in that case, we'll be able to meet and we'll be able to discuss these things in detail. But just to introduce data Earth full protection, you can see against your screen in front of you restricted earth fault protection REF or differential protection. There is one CT in the neutral circuit and three CTs in the line. The relay is connected as you see. Such a kind of protection, that is current based protection, when the neutral is connected through resistance, and as we have discussed, neutral has to be connected with the intentional resistance in the circuit, because uh, otherwise the current will be so large that the stator will be badly damaged. Therefore, this is a must. And whenever you connect a resistor, such a kind of circuit which you are seeing in front of you is useless, because some of the portion of the stator winding will remain unprotected. Portion, certain percentage, that depends upon the sensitivity of the relay, that depends upon the value of the earth resistance that is connected or earth reactor that is connected, and therefore the certain portion of the winding will always remain unprotected. For large 210 megawatt generator, where we reduce the value of the earth fault current to 2 ampere, their 100% winding is not protected. If you connect like this, that means no winding, but a single percentage can be protected by stator earth fault, for stator earth fault protection, if you connect like this. So, just to tell you that this is a useless circuit. This is not what is used. So, what should be used is uh, such a kind of stator earth fault protection. That is a stator earth fault protection which is based on third harmonic voltage, zero sequence voltage, and that gives rise to 100% sensitive stator earth fault protection. My friends, I hope that I have tried to cover what all I could cover in such a short time, as I told you, and as many of the friends who are hearing me right now might be well aware that we have taken some 8 hours or more than 8 hours in covering generator protection. So 1 hour is too short a time. We have to cover some 15 kinds of protection which we had enlisted, and all protections are very useful. Uh, some of the protections are in such so useful that the uh, the the blackout that occurred in the uh, northern grid and northeastern grid and eastern grid in 2012, uh, initiated with load encroachment in the due to distance load encroachment in the distance relays, and ended with probably the pole slipping protection operation. That is, the generator started getting disconnected from the bus due to the operation of pole slipping relays. So pole slipping protection, which we have to discuss in generator differential protection, I mean generator protection schemes, is also a very useful protection. And we will talk about all these protections. We'll talk about all these protections at relevant time. This was my very first trial to talk to you on air. I don't know about the feedbacks. If my student friends give me feedback, I can come to know. Thank you. Thank you very much.
Um, Hello, sir.
Hello.
I
Huh?
have received one question. Hello.
Huh?
Sir, I
Aji?
have received one question.
Aji?
I have received one
Yes.
question.
Please, please
How
speak.
like he is your He is your ex-student from
Ah,
PDPU and
yes,
presently in Torrent Power. His name is
right,
Vaibhav Desai. How line
right.
to ground how line to ground fault on transmission line should be coordinated with generator protection. What are consequences for generator if not done? Can I
Ah,
repeat?
yes, yes. No, I got the question, Vaibhav, if at all he is hearing. Uh, the coordination is done like this, that the first you see with the overcurrent relays of the transmission line, the uh, transformer secondary backup overcurrent and earth fault are to be coordinated. And with that, we have to coordinate the generator backup more relays. Backup more relays, how do we do? Uh, we have to cover the largest line emanating from the power plant. Right? If some generator is there, say Vanakbori power plant, from Vanakbori power plant, 10 lines are going out. The largest line is some 150 km long. So you have to consider the impedance of that largest line, and you have to set the impedance of the more relay for that largest line. K, that is the impedance setting of the more relay. And for that, we have to sit together. And I mean, Vaibhav has to make a call to me. He knows my number mostly. He has to make a call to me, and I can explain to him on call. He has to. We have to draw certain diagrams and have a. Uh, I have to send to him, and he has to send to me on WhatsApp. Uh, Photographs we have to send, and then I can tell him as to how to calculate that value of the setting. You will get the ohmic value Z, and from Z you have to convert to K for the more relay, and that more relay is an offset more relay. So how much offset we have to provide, how much impedance we have to provide. So that impedance, basically, if I want to answer your question, is single line. You have to consider the line length of the longest line emanating from the power plant. I mean, that is the immediate answer that I can give on air. Ethel. Hello, any other question? Any other question? Hello?
Hello?
Huh?
Hello,
Ethel?
sir. I read the question. Ha. In
Huh?
stator or fault protection, if external fault occurs and line CT gets saturated, then system may malfunctions. How we can provide protection against that?
Stator earth fault for external earth fault.
Yes, sir.
Uh,
In stator or fault protection, if external
huh,
fault occurs, then line CT
huh.
gets saturated. Then system may
So,
malfunction.
who is asking the question?
Sorry, I repeat.
Who is
Okay,
asking the question?
question is
Uh,
from Purvesh Walan from Parul University.
Acha, acha. Purvesh bhai, uh, I would want to let you know that you should, I think you should know the way in which the generator is connected. Generator is connected to generator transformer via bus duct. There is a bus duct. Bus duct is a uh, cylindrical shape pipeline which is uh, constructed out of the reinforced cement concrete. So there are three bus ducts. In each bus duct, a wire is going from generator output to the generator transformer directly in the bushing, and then there is generator transformer. It is delta Y connected. So if there is an earth fault on Y side of the transformer, it is not reflected to generator. So that kind of earth fault which is in the secondary of the transformer is not at all reflected to the generator. And in the primary side, the earth fault can just not occur, because you see it is all the three wires are going independently through the bus. So usually I don't think any kind of external earth fault can occur. This backup impedance protection which is used is only for backup line to line fault. It is not used for earth faults, because earth faults are not transferred to the generator. So external earth fault is not possible in case of the generators, because they are all sturdy connections. There is nothing, and the generator is within the room, right? It is not exposed to atmosphere. So I don't think any earth fault, external earth fault would occur, which would give rise to CT saturation. And if you have calculated the value of the fault currents properly for line to line fault also, the CT saturation, if you have used the correct CTs, if you have engineered the correct CTs, then the question of CT saturation also will not arise. I have tried to answer according to my knowledge.
Stop the presenting, so we will see you, sir.
Okay, okay. Thank you all.
हाँ सर, आप जरा स्क्रीन बंद कर दीजिए पहले, तो we just talk not casually.
Shall I come online once again?
Yes, sir.
I am offline now. No, I am
Sir,
online.
just
No, but
yes, sir,
but
you are
I
not
am.
online. You just
But
maximize the
acha,
our
acha.
Google Meet.
I'll maximize. Right. I'll maximize
Yes,
that screen. Correct.
yes,
Right.
yes, sir.
Right. But now, am I seen on the screen? I don't know. Stop presenting.
Stop presenting. Yes, sir.
Yes, I have stopped. And now,
Yes,
am
sir.
I seen on the screen?
Yes, sir. Yes,
Right.
sir.
So
Sir,
this is for the viewers. Is this
yes,
my?
all
Is
viewers
this for the
can.
viewers? I think. Right.
Yes, sir. All viewers can see you now.
Right. So, thank you everyone. Those who are seeing, and let me know how many are. How many of my friends are hearing me? Because I learned
Sir,
through many
and
sources. I learned through many sources that certain viewers are across the boundaries of the nation. Because some
yes, sir.
friends from USA are also seeing me. I think so. Yes, please.
Sir, end of the session, I will get the attendance, so I will inform you. And on behalf of Palo University, I would like to say thanks. On a very short notice period, you have received my invitation and give your very valuable time. And given in this lockdown, you have also given us the very informative knowledge for the generator protection. So once again, sir, thank you very much, sir.
You are welcome. Thank you. Thank
Okay, sir. We will
you.
meet
Okay.
soon
Bye.
when lockdown is open at our Power University. Okay, bye, sir.
Certainly. Okay. Thank you.